Okay, great. Well, what I would like to do for the rest of today is go back to where we had left off on Tuesday talking about linear algebra. You might remember chapter 2 is about systems of linear equations along with matrices. And on Tuesday, I sort of just introduced the whole concept. And wrote down some definitions. And finally, at the end of class, I mentioned that matrices are a primary tool for us to solve linear systems. And next week is really when we're going to be hammering that tool home. Today, I want to mostly talk about matrices and what they are good for, what can we do with them, and we're going to see some kind of interesting properties about matrices at the same time. So I'll do just a very short little recap here. I already handed you the handout with the big recap. This is just a slight little reminder about the definition of a matrix. So just to remind you again from the other day, an M by N matrix is usually going to be labeled with a capital letter like capital A, which is very common. This is an array. It's an array of numbers or functions, and these are going to be arranged in M rows and N columns. Okay, so there's an M and an N. The M is the number of rows. The N is the number of columns. Those numbers are actually sometimes called the dimensions of the matrix. I don't actually like to use that term because it turns out there's something else that's called dimension that we're going to spend a lot of time on in about a month from now. So instead of that, I usually will call the M by N, I will call that the size of the matrix. So the size of the matrix is dictated by the M and the N. So, we wrote down a few examples on Tuesday. Let me write down one more example here of a matrix that we could look at. This one is just a matrix of numbers, and I could draw it out like that. Okay, so 9 and 8, and then 7 and 6, and then 5 and 4. Real quick, can somebody tell me what's the size of that matrix? 3 by 2. And this is the M and the N, getting them straight is kind of the tricky part. This has 3 rows and 2 columns, right? 3 rows this way, only 2 columns this way. So M is 3 and N is 2, right? If we think about it that way. So those are the values for that matrix. Those are going to be the values of M and N. Okay. Again, I had primarily brought this topic up on Tuesday because I wanted to use matrices to work on linear systems of equations. So there was, the matrix of coefficients, and then we made an augmented matrix. I talked about that right at the end of class last time. For the moment today, guys, I'm not going to focus so much on the systems of equations. I just want to talk about what are the things that you can do with matrices. So let's make a list of a few things that we will typically do as operations on matrices. And as always, guys, I'm going to encourage you to interrupt me with questions if anything is going by a little too quickly, or you have a question that you think would be good to get cleared up. I hope you'll do that, right? I know I look like I'm totally excited into it, but at some point it's better if I actually slow down and kind of keep myself under control. So operations on matrices, I'm going to make a list here. The first thing that we can do with a matrix, and it may seem strange why we would want to do this, but it is something called the transpose. We can do something called transpose. We can transpose a matrix. And what this means is this is where we swap the rows and columns of A. We literally just swap the rows and columns of A to obtain what is denoted as A with kind of almost like it's an exponent, but that's really a T for transpose. So we'll be writing it as A transpose. Okay, so the first thing I point out about this A transpose is if I'm swapping the rows and the columns, then the size of this matrix, if my original matrix A is M by N, and then I swap with what the rows are into columns, and I swap the columns into rows, then those numbers are going to also be reversed. So this is an an N by M size. I have to pronounce these letters very carefully. Okay, so in our example from above, A transpose, in this example, the first row becomes the first column. So the 9 and the 8 that was in the first row, I now write it in the first column. The second row becomes the second column, and the third row becomes the third column. So it's going to look something like that. Okay. And this one, of course, is 2 by 3. So the original matrix was 3 by 2. It's been transposed into a 2 by 3 matrix. Okay. So this one is two rows and 3 columns. So I have a question for you guys. Would you consider these two matrices to be the same? If I had a spreadsheet that had data in 3 rows and 2 columns, I'm pretty sure I wouldn't think of it as the same as a spreadsheet that's got data in 2 rows and 3 columns. They're not really the same at all. So even though the numbers themselves are the same, those matrices are not the same. Okay. Would it ever be possible, do you think, for the A and the A transpose to be the same matrix? Yes. Might be possible, wouldn't it? What would have to be true about the size of the matrix if you were going to ever be possibly having A transpose equal to A? One more time? Be the same. The two matrices would have to be the same size, and what would that tell you about the M and the N? The same value. They would have to be the same. In other words, the matrix would have to have, wouldn't it, the same number of rows as columns. This is called a square matrix. I'm going to write that down. Quick little definition here. An N by N matrix. So if there's the same value for M and N, then we're going to call this a square matrix. So that is called a square matrix. And if I had a square matrix in front of me, then when I transpose that matrix, the size of the matrix at least would stay the same. And so you'd have a chance that maybe the transpose of A could be equal to A. That is actually possible. I'm going to give you another definition here to elaborate on that point. So if A is equal to A transpose, again, this can't happen unless we have a square matrix to begin with, right? But if we have a square matrix, and if A is equal to A transpose, then we call capital A a symmetric matrix. A symmetric matrix. This is one where the A is equal to the A transpose. Now, I'm going to write out an example of a symmetric matrix for you here, just so you can kind of visualize one of these. As I'm filling in the numbers in my example, first of all, I'm going to give you a 3 by 3 matrix. It's got to be a square size. I like using 3 by 3 matrices in this class. It's big enough to be interesting, but it's not so big to be that hard to work with. So 3 by 3s are good. I am going to fill in the 9 entries in this matrix using 2 different colors. The black marker is going to be the numbers that I'm putting in here that I can freely choose whatever I want for those values. And then at some point, in order for A to be equal to A transpose, I will be forced to use the red marker to make certain numbers go in certain places. So for example, the first row of this matrix, I'm just gonna fill this out willy-nilly, however I want. Let's just say I go 1, 2, 3, whatever, okay? Nothing wrong with doing that. If this is going to be a symmetric matrix, however, then remember that this first row will get transposed into the first column, right? So the first column of A transpose will be 1, 2, 3, which means that the first column of A has to be also 1, 2, 3, because you're trying to make them equal, you see. If I set it up this way, now the first column gets transposed to the first row gets, they swap. They swap, but there's no change because it's the same numbers. So that's why I'm putting them in red, is that these two numbers must match those two numbers. Okay. I hope I'm not over belaboring this point. On the second row, I could pick, I don't know, a 4 and a 5, right? That's fine, I can do that, but then in order for the second column to agree with the second row, I must put a 5 there. Okay, and then finally that lower right corner can sort of be whatever I want. Maybe I'll just use a 6 for that last entry. Okay, so the numbers that are kind of down here in red in the lower left corner, they were forced upon me by what numbers I had put in the top right corner, because they have to match. In fact, you could look at it this way, guys. It's almost like there's a mirror, there's a reflection, and the numbers up here in the top right are reflecting from the numbers in the bottom left. You see, that's basically what a symmetric matrix is going to look like. Okay. Just to help us with a little bit of notation as we're talking about this, I'm going to add a quick little point here. This is not something that's a huge deal, but sometimes I like to reference certain entries in the matrix. And I'll just say that the entry in row I and column J is denoted A sub ij. So little a sub ij. So you'll see this kind of notation when you're working with matrices, little a sub ij. And just as a quick example here, let's just make sure people are following this. What would be, for this example, what would be the A sub 2, 3 for this matrix that I've got in front of me here? Louder, please. I think I heard it. 5, right, exactly. If you go to row 2, which is the middle row, and column 3, which is the third row, we're talking about that entry right there. And that is a 5. So we would just add that as our result. So A sub 2, 3 would be equal to 5 in that case. See what I mean? So that is the notation. And so for a symmetric matrix, what you actually have, I'll just make this as a room. Oops, use my back to my black marker again. This is a quick remark here. If A is symmetric, then does it look reasonable that the little a sub ij's are the same as the little a sub ji's? This is actually the point. Like A2, 3, which was 5, matches A3, 2. Right? And here's A2, 1. It matches A1, 2. Right? So that's just notationally how you could write this for a symmetric matrix. These numbers that are kind of going along this diagonal from the top left corner to the bottom right corner, they also comprise something that's kind of important. So I'm just going to, maybe I'll just call this a definition again. So another little definition. If A is a square matrix, So it doesn't have to be symmetric, it just has to be a square matrix. But if A is a square matrix, then the entries that are in the form of AII, so that would be A11, A22, A33, those are the ones that are kind of following this diagonal line, right? They comprise what is called the main diagonal of capital A. They comprise the main diagonal. So you'll hear people talking about the main diagonal of a matrix. Now, it's important to realize that only a square matrix has a main diagonal. If we go back over here and we look at something like this matrix does not have, we don't talk about a main diagonal here. We can't really flip this thing, right, or reflect it across this main diagonal line. So anyway, it's a good thing to be familiar with that terminology. All right. And for a symmetric matrix, everything that's appearing to the northeast of the main diagonal should be a reflection of the entries that were filling up the southwest part of that matrix, right? What's in the upper right corner should simply be a reflection of the lower left corner. Exactly. That's right. Okay. By the way, there's another, while I'm at it, there's another definition. Sorry for all these definitions. It's mostly pretty elementary terms. They're not that deep, but still, it's a lot to kind of keep track of. But there's actually also something called skew symmetric. So if A transpose is not quite equal to A, but is equal to the negative of A. Now, negative of A, by the way, that's just what you think it is. It's the matrix where you put minus signs through all of the entries of A. So you just add negatives to everything. If A transpose is equal to negative A, then we call capital A skew symmetric. Then it's skew symmetric. So it's not quite symmetric, but it's kind of close. But there is this minus sign issue that comes up. So let's write out an example of a skew symmetric matrix for ourselves. Maybe this time I'll go up to a 4x4. It has to be a square size again, that's for sure. And I'm going to start filling this out kind of randomly, and then let's see if it's actually okay. So if I start with the first row and I say, I'm going to do 1, 2, 3, 4. When I transpose that, the 1, 2, 3, 4 will go into the first column. However, what I'm supposed to get when I transpose it is just the negative of what was already in the matrix A, right? So whatever the first column of A is, the negative of that is going to be, well, 1, 2, 3, and 4. What I'm trying to say is all of these entries, this should be a -4, this should be a -3, this should be a -2, and this should be a -1, except that I already put a 1 there. And so I can't put a 1 there because 1 is not the same as -1. What is the only number that you guys know that is the same as its own negative? No. 0. You have to use a 0 there, guys. That's the punchline. For skew symmetric matrices, you must have zeros on that main diagonal entry. Okay, so guys, if you transpose, well, let's fill out the rest of it. All of this diagonal would be 0. And then again, I can do 5, 6, and 7. And then this will be -5 and -6 and -7. That's an example of a skew symmetric matrix. If you transpose this matrix, remember what you're really doing is flipping it across this main diagonal when you do that, right? When you transpose, that's what happens to the matrix. The entries get flipped across that diagonal. So for skew symmetric matrices, when you flip this matrix across the main diagonal here, the numbers in the upper right corner have to become their negatives in the lower left corner. The transpose of this matrix would literally have all the negatives in the northeast corner and all the positives in the southwest corner, which is the negative of what's currently there. And that's how the definition is written. So that's a skew symmetric matrix. Does this make sense? Please, Diego.
Wait, how come you put all zeros like throughout the?
Yeah, the reason is that if you try to use any other number there, then when you take the transpose, see the numbers that are on the main diagonal, when you transpose them, they don't move. They're kind of pinned to the diagonal spots. This is like an axis of reflection. So if something's already on this diagonal, it can't move when it's flipped, but it's supposed to pick up minus sign. Right? In fact, what we could do here, guys, is we could just say Aij is negative of Aji. This is actually the condition. Right? Similar to the one for symmetric that we did a few minutes ago. And so if I put I and J the same, then what do I have? Aii equal negative Aii. There's only one number that's equal to its own negative. It has to be 0. That make sense?
Yeah.
Sweet. Yeah, great. Yeah, so these are the symmetric and the skew symmetric matrices. There are several other important sort of what I'll call special matrices. I'm gonna go back to the Canvas page here. I've pulled up our screen, our Canvas page, and I want to go again in the files folder down to special handouts. Okay. Don't worry about writing all this down because it's going to be in the homework, so you will not miss this. But there is a document called Special Matrices Handout, and I'm going to open this one up right now. Maybe. Here it comes. And there you see summary of special n by n matrices. The first one is the symmetric matrices we just talked about. Then we have the skew symmetric matrices. What I did here, I wrote down an example of each of these, kind of using the general notation. And there's actually a few more of these that sort of fill out a whole page here. So I'll ask you to look at this. There's upper triangular, lower triangular, and diagonal matrices. By the way, these are all square matrices. They're all n by n. And so this is just a little one pager of some very basic matrices that you have out there. But what I wanted to point out is that if you look at the homework that's due tomorrow night, go to the assignments real quick. And so the homework that's due tomorrow night, which is assignment number 3, there is, see, I put the special matrices handout right there in the assignment next to this 7-minute video. So I would like you don't need to take notes on the video because the notes would be the handout, which I've already made for you. You just need to watch it. And in that video, I'm going to talk about this again. So if you want to listen for 2 more minutes, by Saturday night, you're probably going to be missing the sound of my voice. You can go turn on my YouTube channel. You'll have me right there. And I'll also talk about the upper and lower triangular matrices, the diagonal matrices, and so on. So yeah, so just please watch that video for me over the weekend. It's pretty basic stuff as something to kind of supplement what we're doing right here. Questions? Oh my goodness, all of this is under number 1. Operations on matrices. We can do transposes. Well, I want to get to number 2 and number 3 before we take a little break today. So let's do number 2. Move on to another thing that we can do with matrices, okay? And this one is just going to be, we can do calculus. We can do calculus on matrices. So what I mean by that is, well, we can do derivatives. There's anything that you can think of from calculus, well, we can do it here with matrices. So integrals, we can take limits. I'm just gonna put ... Like this can go on and on. I've hit some of the highlights of calculus already with that list. But you can basically take a matrix and take its derivative. You can take a matrix and take its integral. Now, this won't be so interesting if it's a matrix of numbers. Remember, I talked earlier, a matrix could be an array of functions as well. So maybe we should write down an example of this and just see kind of how this might look. Maybe for this example, instead of capital A, I will use a B just to kind of mix this up. And I'm gonna make this B really look like a function of some variable. So I'll use a T for that. And let's just make up something here. So let's make it a 2 by 2 matrix and e to the 2t. And then maybe here we have 3. And here we have negative sine of t. And here we have 4t squared, something like that, just to kind of have an example in front of us here. And so I could ask you to take the derivative of this matrix. And the question is, well, how do you do that? Well, for any of these concepts, the way that you apply the calculus property is you just do it individually, slot by slot to each position in the matrix. So I like to refer to this as slot by slot. This is going to be the method to do it. All right. So if I give you this matrix and I ask you to take the derivative of it, so I'm really asking you to do 4 derivatives. I could really play with my calculus students and tell them that I'm only going to ask you one homework problem. Take the derivative of this one matrix, and it's a 5 by 5 matrix or something. And then what they're really having to do is do 25 derivatives, right? You have to do a derivative in each slot. So here we're only going to do 4 slots, obviously. Let's just do it. Let's just write out what it would be. So I just have to practice my differentiation here. The derivative of e to the 2t, well, that's 2e to the 2t. The derivative of 3 is just 0, because it's a constant. Let's see, the derivative of negative sine of t, I believe that would be negative cosine of t. Let me know if I'm getting any of these wrong. And then the derivative of 4t squared, I believe, should be 8t. That would be the derivative of that matrix. Similarly, if we wanted, we could take the integral of that matrix. So I could do the integral of b of t dt. And again, I'm just going to do it slot by slot. I'll end up with a 2 by 2. Now I have to be a little careful here. This is an indefinite integral. There's no limits of integration provided. And so that means that we're actually talking about antiderivatives. And we remember that with that, we must always add plus c on the end of these calculations. The antiderivative of e to the 2t would be 1/2 of e to the 2t, but there would be a plus c on the end of it, except that there's actually 4 different plus c's that are going to show up. And so I might as well use some subscripting to make it clear like they're not all the same constant. So c11 is like my constant of integration here. Yeah.
It would be incorrect to just have a plus c outside matrices.
Yeah, it would be better to do, I mean, I suppose you could, but you would have to make it clear that this was a matrix and not a number. At that point, that plus c over, because you cannot take, so one thing that's definitely a no-no is you cannot take a matrix and add a number to it. It's like they aren't compatible. They're not the same kind of object. So it's actually probably, it's a good question, but it's probably less confusing if we just kind of do everything inside the entries here. Yeah, good point. The antiderivative of 3, that would be 3t, and I'll write plus c12. The antiderivative of negative sine of t would be cosine of t, and to that I'll add c21. And then the last entry is the antiderivative of 4t squared, which by the power rule backwards should be 4/3 of t cubed plus c22. And these subscripts are actually lining up with the notation that I had explained earlier about rho I and rho j having subscripts of aij. So I'm just using that same subscripting notation there. Now, you could, of course, have an integral that includes limits of integration. If that was the case, then you would just be evaluating each of these four antiderivatives from the lower limit to the upper limit and coming up with an answer. I think the homework problem on this, which will be for next week, you'll have one to do that does have limits of integration in it. So you'll just have to evaluate it the way you would in calculus. My point being here, guys, is there's not a lot of creativity with this. It's nothing like earth-shatteringly new. You're just taking the matrix and doing calculus slot by slot. That's all it is. Okay. Everybody with me? Okay, one more thing I want to cover here before we take a little 10-minute hiatus is number 3 in my operations on matrices. We've talked about transpose, we've talked about calculus, but calculus is almost getting ahead of ourselves. We actually should also talk about just algebra. Matrix algebra. Right? Yeah, and when I'm talking about algebra, I just mean like really, really basic algebra. I'm talking about addition, subtraction, right? If I want to add matrices or subtract matrices, we can also do multiplication. And then there's something called scalar multiplication. So I'm going to write the word scalar next to my multiplication dot here. And I'm going to leave it at that for now. You might be wondering, oh, wait a minute, I usually think about addition, subtraction, multiplication, and division. So I'm not putting that on this list. There's a reason, and the reason is we cannot divide matrices. Illegal thing to do, right? There is no such thing. We're gonna try to find an alternative to that next week, but for the time being, yeah, we can't do division of you can't divide one matrix by another. It just doesn't make sense. But all of these other more familiar operations, they will work. I want to point out that with addition and subtraction, so this would be, A plus or minus B, you're adding or subtracting two matrices, that this is done only where A and B have the same size. Okay, they have to have the same size. I can't take this matrix and add it to this one. They're not compatible sizes. The way that the addition works, or the subtraction, is slot by slot again. So you just go through entry by entry through the whole matrix, adding or subtracting the particular slots. So that is done slot by slot. And guys, I'm going a little fast here. I do recommend that if any of this is a little bit foggy, that you either check in with me during my office hours or watch some videos on this. This is not rocket science. But if you're confused, you're confused. And that's the way math always is. Like, it's very hard to understand it until you realize, oh, that's all it is. And then it's like suddenly the light bulb goes off and it becomes very easy. So I don't want to, make it sound like, it's supposed to just be automatically clear. But I am going a little bit quickly through this. The scalar multiplication is also slot by slot. You just do the natural thing. If I put a 2 in front of a matrix, all that means is I'm going to double every single entry of the matrix. Just exactly what you do. You just throw that constant all the way through. In the same way that when you take a -1 times a matrix, you're just putting a sign change through every single entry of that matrix. That's how that works. So I think this is good, this is good, this is good. It's all slot by slot. It's all very natural. But now we come to the one that's a little bit weird. And that is this one right here, regular matrix multiplication. And some of you have probably seen it already, and it's not anything that's really that hard. It's just a little surprising. Matrix multiplication is not done slot by slot. And in fact, matrix multiplication does not even assume that the matrices have the same size. They do not have to. So I'd like to take a moment And this one, I actually will do an example. I like to spell this out just a little bit. And once we're done with this, we will take a little break. So make multiplication of matrices. This is really what this dot right here is talking about. Please don't confuse that with scalar multiplication. Scalar multiplication is where you take a number times one single matrix. What I'm talking about here is two actual matrices. Okay, so let's set this up. So given an M by N matrix, capital A, and an N by P matrix, capital B. Okay, so I would like to multiply A times B. Notice what I'm handing you. I'm handing you two matrices that have different sizes, but there is one common thread here, and that is this N value. What that means is that for the first matrix, the number of columns, right, the number of columns of A is being set up to match with the number of rows of B. Not being set up, it's being required, right? It's required that the number of columns of A matches the number of rows of B, right? Then we can form, or we form the M by P matrix AB. So the size of the product is still another set of numbers, right? So we go from M by N and N by P. We're going to combine them together and get an M by P matrix. How in the world do we do that? By taking dot products. Oh my goodness. You guys remember dot products from Calc 3? You have some vectors and you want to dot them together. There's a sort of little simple little calculation you do. Dot products of, and I'm going to write it this way, guys, rows of A dotted, and those are vectors, dotted with columns of B. And that's also a vector. So we're going to do dot products of the rows of the first matrix with the columns of the second matrix. Let's do an example of this one. Make sure everybody's kind of with me on it. All right, so let's get my example here. Let's do a quick example, all right? So let's take this one. I'm going to take A to be 1, 2, 3 on the first row, and then 4, 5, and 6 on the second row. And then for the matrix B, by the way, what is the size of this matrix? 2 by 3, excellent, okay. And then for the second matrix B, I'm going to use -1, 0, 2, and 1 on the first row, and then the second row is going to be 2, 1, 1, 0, and the third row is -1, 3, 0, and 1. And help me out, what's the size of this one? 3 rows and 4 columns, right? That's a 3 by 4 matrix. So the first thing I want to ask you is it legal for me to calculate A times B? We come back over here, the A has to be M by N, and the B should be N by P. These two numbers have to match. Well, if I look at it, for A, I have a 3 here, and for B, I have a 3 here, and those do in fact match. Because of that, I can calculate A times B. Let's talk about that. Can somebody tell me, before we actually write out the matrix, can you tell me what the size of that matrix will be? M by P, right? M here is 2, and P is 4. So this is going to be a result that is 2 by 4 as a result. And so let me get myself set up. I have to have 2 rows and 4 columns. Okay, and now I'm gonna try to just explain, I'm gonna do this once. And if it's not enough, or if you need to reinforce it, your weekend assignment is gonna be to go on YouTube and watch one of the 5,000 videos about how to do this. But I will do it real quickly right here with you. For the 1-1 entry, if I want to fill in this 1-1 entry right here in the upper left corner, the way I do it is I take a dot product of row 1 with column 1. So row 1 of A is this one, 1, 2, 3. And I dot that with column 1 of B. So I'm taking the rows of A and dotting them calculus-wise with the columns of B. So the dot product here would be 1 times -1 plus 2 times 2 plus 3 times -1. Does that seem familiar, how the dot product works? So you get -1 plus 4 minus 3. What's that add up to? Should be 0. Yeah, this is actually a 0. And that's the number you put down there. So the 1-1 entry of A times B is actually 0. Clear enough? If I want to move to the right, I want to do the 1-2 entry. Well, I still take row 1 of A, but now I'm going to dot it with column 2 of B. Okay, so I'm gonna take 1 times 0 plus 2 times 1 plus 3 times 3. So that's 0 plus 2 plus 9, which adds up to 11. Exactly. Okay. Let's go to the next one. The 1-3 entry, I'm gonna take row 1 and dot it with column 3. That's gonna be 2 plus 2 plus 0. That adds up to 4. And lastly, when I go to the 1-4 entry, I have to dot row 1 with column 4. And I have a 1 plus 0 plus 3, which is 4. That makes some sense? That's for row 1. For row 2, what do you suppose you'll be doing differently? Take the bottom row of A, which is the 4, 5, 6, and do all of those dot products again. I'm gonna give you guys 60 seconds to do them yourself, and let's check answers in about a minute. Row 2. So I'm taking 4, 5, 6, and I'm dotting it with each of these 4 columns, and they should be coming up with 4 different numbers, or 4 numbers for that bottom row. Anybody think they might have it yet, or am I rushing too much, or? You wanna try it, Arlene?
Yeah.
Sure.
0, 23, 13, 10.
Can anybody confirm that? Anybody get that? Seeing some people nodding in the right direction. Excellent. Yeah, that's what I got too. That's great. If all of us got the same answer, it must be right. Well, that does look pretty good. Okay. I hope this makes sense. I will tell you, so I've taught this class quite a few times. Somehow there's always a little handful of people that I notice even by weeks 10, 11, and 12. Somehow we need to be doing matrix multiplication and we're having trouble with that. If this is going by a little quick for you, like I said, this weekend is a perfect chance to slow down. The homework for Tuesday is pretty short and easy. It's going to have some of this on it. Really make sure you've got this solid. This is not something you want to be fumbling around with in November, trying to figure out, because we're gonna have a lot of other stuff to be learning at that point. But yeah, this is just pretty basic technique for matrix multiplication. Okay. I have to tell you guys, you know, when I was growing up, when I was a kid, I'd come home from my high school and my mom would have the soap opera on television. And I was kind of tired from my day of school, so I was like, "Oh, I think I'll just watch it with her." And so I was watching this program. It's called General Hospital, and I would watch this soap opera with her, and I would sort of fall halfway asleep. But at the end of the episode, they always have some way of hooking you back in to come to the next episode the next day. Like the music starts getting dramatic, something about as exciting is about to happen. I realized after I was watching this soap opera for a few years, this might not be a bad approach to the lectures for math. I should make sure that I get everybody to come back to see what's going to happen next and get you excited to maybe come back in 10 minutes to learn the next part of the dramatic story. So I'm going to do that right now. I'm going to throw something up here that may seem a little bit like a strange question, but I would like to ask you guys, what is B times A in this problem that we just wrote down? We calculated A times B. Notice that A is the one on the left here, and then B is the one on the right, and we calculate A times B. My question is, what if I tried to calculate B times A? Keep in mind, B was, what was it, 3 by 4? And A was 2 by 3. So my question is, first of all, does that work? You know what? The sizes are wrong. If this is my M and my N, then this would have to be the N, and it's not matching, right? These two do not match anymore. And so to use a phrase you would have probably used in calculus quite a bit, we would have to say, it does not exist. You cannot calculate B times A, right? So this is impossible. And so actually, what that tells us is that in general, my friends, this is worth knowing. In general, with matrices, it is not true that A times B has to be the same as B times A. They are not generally equal. In fact, they are almost never equal, even if they both existed. So let's say that A was 3 by 3 and B was 3 by 3. Then A times B would be 3 by 3 and B times A would be 3 by 3. But you know what? They still, unless you were very, very lucky, as in like win the lottery kind of luck chances, you would find that they're not the same. Matrix multiplication, in other words, matrix multiplication is not commutative. This commutative word, it's kind of a property from algebra that sometimes gets used. For numbers, of course, it doesn't matter what order you multiply anything in, but for matrices, it makes a huge difference. And so what are some of the ramifications of that? Well, I will scribble a couple of things over here. For instance, if I wanted to calculate, I'll just put this as examples really quick. But we will take a break in a minute, but let me just finish this thought, because this is actually pretty cool. Actually, I probably wouldn't be standing here in front of you if A times B was always equal to B times A. That's because I did my PhD on something called non-commutative algebra. I spent years studying algebraic systems where the order that the objects are applied in makes a difference. And it's a totally weird world to live in. And here's a really good example of where you see that kind of behavior, right? This is a non-commutative algebraic system. matrix multiplication is a great example of it. If everything was always commutative, I wouldn't have had a PhD to write, and if I didn't have that, I probably wouldn't be here. So anyway, I'm kind of grateful for weird, funky things like this that happen. And it leads to other funky things, like what if you wanted to take a plus b and square it? Well, of course, the way you would want to pursue that is to just multiply a plus b by itself, which is correct. And then you would want to FOIL this out, and you take a times a, there's no problem with that, and then a times b for the outer term. The inner term would be b times a, and the last term would be b squared. But the point is, you cannot simplify it any further. You can't combine the two middle terms, which is what you normally would have done in your high school algebra class, right? Another example, if I just have a mishmash of letters here, a bunch of matrices, I don't know, something like that. You cannot simplify it. You can't say, oh, well, that's actually a to the fifth times b to the fifth times c cubed. You can't do that, right? This cannot be simplified. You just have to live with it. Leave it the way it is. Or I could show you the one that gets people in trouble the most. And I should, because it does happen a lot in 250B. What I see people do, okay, so I'm gonna put this down, and your job is to not let it be you that does this bad thing right here. I will see people showing me some calculation, and they'll have a matrix here, I'll call it B, and they'll have a matrix here, let's call it C, and they'll be equal to each other. And then what I'll see the student want to do is, oh, I want to multiply both sides by A. And what I'll see them do is, that seems reasonable, right? You can take an equation and whatever you do to the left side, you do it to the right side. So I'm going to multiply both sides of this by A, and I'll see them do this. And that is not correct. What I just did in blue, because what I just did, guys, is I multiplied on the left side, I put the A on the left of the B. But then on the right, I put the A on the right of the C, rather than what I should have done, right? What I should have done, let me get out my red pen here. Right, what I should have done is if I'm gonna put the A on the left of the left side, I should also be putting it on the left of the right side. So this should have been AC, which, as we've just discussed, is not necessarily the same as CA. So it's really important to keep left and right straight. This one is easy to, if you're not really focusing, you can easily trip yourself up with that. So just something to kind of look out for. Try to make sure that you're careful about keeping matrices in the right order. That's all. Okay, guys, let's take a break for about 10 minutes. We'll only have 15, 20 minutes to go at the end. It'll be a short little second part of our class. But go ahead and get some fresh air if you want to step outside, get some water, run around the building. I know it's too hot outside to go outside, I think. But we'll start back up in about 10 minutes. So, but I am having on Saturdays. Yeah. And, or unless you have something you want to ask me right now, I can do it really quick right now.
Yeah.
I'll just think.
So.
I think that's it here now.
Like,
Good.
This part where I got like. I know that there's some like, just ignore everything. Just look at this, right?
The
First row, first call.
Oh, yeah, that's what I wanted to see, obviously.
What's the first one we were in?
One.
What's the first one?
This is number 11. That's right.
So you, so it's like, someone else has one negative, so you don't put- so it's-
Yeah, good job. That would be, let's see, let's redo, maybe if you could erase that, just that, thank you so
I'm
much.
like, I had a question. That's a matrix, right?
Yeah, these are all matrices. They're not numbers, we're not in a numbers world here, this is a matrix world.
I thought I mean, if it's a 2x2, right?
Yeah, if each of these is a 2x2 matrix,
It
you can
works.
multiply them together, but this will not be the same as that.
Yeah.
Unless you're really lucky, you'd have to get really lucky for that to be the case. Thank you so much, I really appreciate it.
One time there.
But we're still in the first column. Something still staying in the first column. And now you look at the blue row. Yeah.
Three times.
Yeah.
No, one time, two times one.
First, which column they're right.
Four, try. So for the second, this one. Zero, 20 times.
It's like a little. So what am I saying, right? So you just between those. What am I saying? Covering. It is.
One. So four times negative one, five times two, six times negative.
That's what we have in the first page. What would you reply about the units?
And then, oh, then
I'm sorry.
four times zero.
As soon as I have a little more clarity, I want to take it.
Based on your. Get to meet it, like, at least about the seats around the room.
Well,
That's fine.
it's pretty tight, pretty tight.
This position is two, right? The row. Oh, two, one. Two, one, two, then one. Would be the zero. Yeah. I was writing it down. Two, and one would be good.
You're feeling better?
Yes. So we
That's good.
Without the credit.
But
There we go. Compare everything to
I
something.
usually get some plugged at some point, but it's usually the spring hits me worse normally. I think I just get run down by the whole year and my body's just like, no, I need sleep. Usually I do okay in the fall for a while anyway. We'll see.
Do you recommend these three blue and browns for the liaison?
I'm sorry?
Do you recommend Will Lord Brown's videos? Are you familiar with that YouTube channel?
No, not in the least. It's good visuals.
Yeah.
Oh, okay.
It's just I don't know, I just know my was Steve Brown, right?
Is he a professor somewhere?
Retired, I think.
Okay. Those people have a lot of free time.
Yeah.
Do that kind of stuff.
But he's got a very interesting. I mean, I used to watch him like before any of this, so I still don't understand it, but he has a series on linear algebra.
Okay, yeah.
And like starts with like linear transformations before getting to matrix multiplication as like a visualization.
Yes, that leads into the question of why do we multiply matrices the way we do? Yes, that, I was going to make a comment about that. I was gonna make a comment about that, so.
I didn't know if it was a common, like if that was a name that he knew.
Not myself, no. Can't say. No. Hey, guys, well, we only have about 15 to 20 minutes left here, and I'd like to try to finish this sort of crash course on matrices today, so that next week we can come back and focus on the linear systems again. I've got one sort of non-property of matrix algebra on the board already, which is that you cannot switch the order in which matrices get multiplied together. But there's a lot of properties that do work. And I would like to show you a list of some of the properties that do work. And let me see if I can get my screen back up, because I wanted to comment that out again. It's gonna take a second for this thing to, sometimes it gets a little bit tired on me. I'll let that thing, oh, there it comes. Okay, good. So let me go ahead and I'll make a list here of some properties of matrix algebra. And there's going to be 10 things in this list, guys. Properties of matrix algebra. So guys, we already have one property that doesn't work, which is the matrix multiplication. But there's a bunch of things that do work. And in order to talk about all of these, I actually need this special matrices handout again, which I pulled up earlier, but I didn't go all the way to the bottom of it. So these last two on the bottom, number 6 and number 7, are going to be kind of important for this in a second. So for example, let me make this first property here, guys. If I take A, which is m by n, and I add the what's called the zero matrix to it, I just get A again. So this is not anything earth-shattering. Guys, the zero matrix, which is number 6 on this handout that I pulled off of Canvas again, the zero matrix is literally a matrix filled with nothing but zeros. If you add that to any other matrix, well, it's just going to give you the other matrix right back to you, right? So no surprise. It's the same thing that happens when you add 0 to anything. It just doesn't have any effect at all. Okay, let's go and write down a few other properties. If I take the number 0 and multiply it by my m by n matrix A, so now this is a scalar multiplication. And the scalar is 0. So I'm going to do slot by slot scalar multiplication and throw that 0 all through the whole matrix. What do you think I'm going to get? All zeros, right? It's actually the zero matrix, right? It's completely going to get zeroed out fully. No surprise there. Okay, the next one, again, there's 10 of these. The next one is just if I have 3 matrices, A, B, and C, the good news about matrix multiplication is it does not matter how you parenthesize the product. So if I have 3 matrices, A, B, and C, it doesn't matter if I first multiply A times B and then do C, or whether I first do the BC and then pre-multiply it by A. The nice thing about this is you can be sloppy with parentheses. Or in fact, you could even just write ABC. And people would know that it really doesn't matter whether you're really doing the A times B first and then the C, or whether you're doing the BC and then pre-multiplying by A. The important thing is we're not switching the order of anything, right? The left and right positions is not changing, but here we're just saying, look, the parentheses don't matter. This is a real pain to prove. I think I have it proved in the book. I remember writing it, typing it out and thinking the publisher is gonna hate this, and I had to keep it as short and sweet as I could. It's not very enlightening and it's a lot of notation, so we're not gonna do it. This is called, there's a name for this. This is called the associative law. So matrix multiplication is associative. It's not commutative, but it is associative. It is also nice to know that matrix multiplication is distributive. So if I take A times the quantity B plus C, that's the same as A times B plus A times C. And going along with that, we could have the addition first on the left, so it could be A plus B first, and then that's multiplied by C. That gives me AC plus BC. So just the same way that it would work for numbers, it works for matrices as well. Notice that I'm not switching the order of anything here. So these two together, they're both considered the distributive law. So it's worth writing that down, but we can kind of, our intuition is gonna guide us to doing stuff like this, and it's perfectly safe to do that, okay? I've got a few more for you here. Number 6 is the one that involves this identity matrix. So if we go back to the handout here, guys, the identity matrix is actually a square matrix, and it's written as I sub n. And so I've got I3 as an example here. What it is it's a matrix that has almost all zeros in it, but down the main diagonal, remember that main diagonal we talked about that goes from the top left to the bottom right? It's filled with ones. That matrix, as it happens, kind of behaves the way the number 1 behaves. So if I take any matrix, let's write this down. If I take any matrix, M by N matrix A, and I multiply it by the identity matrix, I just get A back again. It's like if I multiply a number by 1, it doesn't change that number. Now, if you don't believe me necessarily, you can just play with a little example. Here's a little random 2 by 2 matrix. You can multiply that by, let's say, the I sub 2 matrix. And we just learned how to do these dot products. You know, we go across the rows of the first matrix and dot them with the columns of the second matrix. I promise you that if you do that with the identity matrix there, it has no effect on the matrix on the left. You just end up getting the matrix that you started with again. The dot products are super trivial in that case. Nothing interesting happens. So this identity matrix is like multiplying by 1. So, and actually you can put it on either the left or the right. So number 7, if we had an M by N matrix A and we left multiplied it by the identity matrix, we again would get A again. Notice here I wrote it as I sub M. This is to make sure the sizes are going to work, right? The number of columns of the first matrix has to match the number of rows of the second matrix. So this is the second matrix with M rows. So the identity matrix would need to have M columns in that case. So these are not typos, guys. The N is here and the M is here. They do need to be the correct sizes. Yeah, but either way, it doesn't matter. When you multiply by an identity matrix, nothing happens. Basically what we're saying. Okay, everybody with me? I got three more for you, and these three, I'm gonna get your help with, I hope. What would happen, guys, if I took a matrix and I transposed it? These have to do with transpose. If I take the transpose of A, and then what would happen if I transposed it again? Remember that transposing is where you swap the rows with the columns. So if you did that, and then you did that again, you would get back to A again, right? You would get exactly, thank you, you'd get back to the original matrix A, for sure. So a double transpose is just gonna cancel out, right? Number 9. What if I added two matrices A and B together and then transposed what I ended up with? So we have a question of what would that be? Or could we calculate that in a different equivalent way? Instead of doing all the addition first and then swapping the rows and columns at the end, would there be another way to do it that would lead us to the same place? The same answer? Do the transposes first. Yes, exactly. We could do the A transpose and then the B transpose, do them separately, and then do the addition after they've already been transposed. Perfectly safe thing to do. Yeah. Okay, that's another one. And then number 10. I know a lot of these are not all that exciting, but just want to get them into the notes here. What would happen if we took A times B and transposed that? Anybody have a speculation on maybe what that would turn out to be the same as? A transpose times B transpose is the natural thing to guess. I'm gonna write it in red if that's okay. Sorry, I'm red penning you already. No, that is the natural thing. That's what I thought. That's what I thought it would be too. But let me show you something. If A is M by N and B is N by P, those are the dimensions we used earlier, then A times B, we talked about earlier, would have to be M by P. And so finally, on the left side here on number 10, if we transposed that, we would finally end up, right, with P by M size. Okay, so here I'm just working out the sizes of these matrices. Now, what would have happened if we did the A transpose and B transpose separately? So the A transpose, I'm gonna put it here, the A transpose would be N by M, right? We swapped the dimensions. And the B transpose would be P by N. Are we allowed to calculate A transpose times B transpose here? It actually doesn't work to even calculate it because this number, or these two numbers here, do not match. Right? The columns of the first matrix does not match the rows of the second matrix. So actually, that's why I have this in red, is that this actually doesn't even have to make sense. But is there something up there that would make sense? B transpose, that's this one, times A transpose. And what would be the size of that? P by M, which is exactly the size that we were expecting here. Turns out that is the correct formula. Oh, and another example of where this non-commutative multiplication is kind of getting us screwed up a little bit, right? It's a little tricky. So yeah, this should be B transpose A transpose. That's really what it needs to be. Okay. So just a laundry list of some properties of matrix algebra there. That last one's a little bit surprising, but hopefully it is okay. I've only got about 5 minutes and I'm gonna take attendance also before I get done here. But I do want to wrap up today by tying this back in briefly with linear systems. We've been doing basically just a bare bones matrix theory crash course today. But I want to tie it back in with linear systems and show you one really cool point. A linear system, just to recall from last time, this goes back to Tuesday. What does it look like? It's a bunch of linear equations, right? Notationally, I could write them like this: a11 x1 plus a12 x2. I do think this is worth writing down, although it's a little bit tedious. I suggest that it is worth writing it down. The a1n xn on the left side and then equals to b1. That's a linear equation. I'll remind you that the x's are the unknowns. The a's are just numbers, the b's are just numbers, but we have several of these. It's a whole collection of them. So on the second equation, maybe I have a21 x1 plus a22 x2, a2n xn equals b2. And we can go dot, dot, dot. I won't write too many of these out. The last one, maybe the mth one, would be a m1 x1 plus a m2 x2 and plus dot, dot, dot up to a mn xn equals bm. This is the one and only time I'll write it down. The way a generic linear system would look. And on Tuesday, I actually even talked about the matrix of coefficients for a linear system. That would just be all of these aij's. And they form a matrix, right? And then we talk about augmenting that matrix by adding on one extra column with the b values kind of on the right side of that bar. Perfectly fine way to take your linear system and write it in terms of matrices. That was kind of the whole point, actually. Right, that's why we started talking about matrices. But I would like to show you something different right now. Because when I look at the left sides of all of these equations, you know what they look like to me? a11 x1 plus a12 x2 plus dot, 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 right? It looks kind of like I took a dot product of some a's with some x's. The question everybody should have somewhere right about now is, why do we multiply matrices in this weird, crazy way, especially when bad things happen, right? Well, the answer is that actually that dot product matrix multiplication does make an appearance even here. What I'm going to do is rewrite this, not using an augmented matrix, but by using a matrix multiplication. And I'm going to just take an extra minute, guys, to get this done, if that's okay. It's super cool and leads me nicely into my soap opera approach to finishing off the week here. I'm going to write out my matrix of coefficients. But instead of just augmenting it with a dead column of the right-hand side values, I am going to multiply this matrix. Now, keep in mind, this matrix is m by n. You can see there's m rows, there's n columns, and I am recognizing dot products going on the left side. a11 times x1 plus a12 times x2 and dot, dot, dot to a1n times xn, and that should all be equal on the right side to b1. And then the second row, a21 x1 plus a22 x2 plus a23 x3 and so on, that all equals to b2. That's my second equation in my system. And we just go dot, dot, dot like that all the way till we get to the last one. The last one here is bm on the bottom. Check me out on my sizes. This is m by n. This is n by 1. And my final answer was m by 1. One column. And here we have n rows. Here we have M rows. You see that? This is just another way of writing our linear system using matrices. And what is it? It's literally just capital A times my vector of unknowns. The x's are the unknowns. I'm gonna draw them as a vector. And on the other side, I have another vector of the b values. You with me? How would you normally solve this for the unknowns, guys, if you wanted to solve for x? Say it again. Divide by a. If I was like in grade school and I had an equation, 5x equals 8, and they ask you to solve for x, you're gonna divide by 5. So what, are you the one who answered that, Eric?
Yeah.
So what Eric would like to do is divide by a. Let's go back to our list of operations on matrices. We had transpose, we had derivatives, we had integrals, we had addition, we had subtraction, we had multiplication, we had scalar multiplication. What was the one thing that I said we cannot do with matrices that all of a sudden we would like to do? Divide by a matrix. Oh my God, we can't do it. We cannot solve it quite that way. Next week, though, I'm going to explain how we get around that problem. We can actually do it. I'll show you next week. That's it for the math. I want to really quickly run through the names, guys, because I'm going to write down anybody's name who's not here. So make sure, I'm going to do this really quick because I'm out of time. Just shout here if you hear your name, okay? Is Gabriel here? Got it. Eric?
Here.
Robin?
Here.
Yasmin? Thank you. Alex Escobar? He's not here. Fatima? Here. Thank you. Dylan?
Yeah.
Kevin?
Here.
Helena? Here. Arlene's here. Caitlin? Is Caitlin here? Okay, no Caitlin. Amin?
Me?
Joe? Sukman? Thank you. Andrew?
Yeah.
Brody?
Here.
Chris? Loiza? Janelle? Thank you. Catherine? Josh?
Here.
Leon? Seth? Diego? Clinton? Armand?
Here.
Roland?
That's like the highest.
Okay, Kian
Here.
and Kathleen? Ian? Kevin?
Basic.
Alyssa? Thank you. Yolanda? And is Abdullah here? All right, thank you guys. Have a great rest of your Thursday.
So easy.
I am terrible at physics. I'm glad. But it's so hard. Yeah.
That's real computer science. I don't like it.
You don't like it?
You want to help me out? Hey, thank you. I'd appreciate that.